Second lag here, just a second.
All right, I see you.
Okay, we're live.
We're doing it? All right. Welcome, everybody, to the July 14th General Meeting of the Los Angeles Astronomical Society. I am President Keith Armstrong. Celebrate me, all of you, celebrate me.
Yes.
There it is. Now it's at least west of the Mississippi. We're crushing it. Okay. As is tradition, the first thing that we like to do is call out any new members that haven't been to a general meeting thus far. Do we have any here in house? Of course, at the very top. All right. Well, you got to explain why you're here. I know. Seriously, I know. All right, explain.
So I'm Michael, and I love space.
Perfect. That's the only requirement. It's good. Somebody has to catch me if I fall down these stairs. Oh, we got one more. Okay, awesome. We'll do it like this. Team effort.
I'm Dave. I caught the astrophotography bug just last December, and so now I'm here.
I'm sorry for your loss. Speaking on behalf of your dollars. What about out there in Zoom land? I see mostly familiar faces, maybe a couple that I don't recognize. Anyone else like to introduce themselves? And we have another one in-house too, of course. I got to clump you guys together. I need like a border collie or something. You're not sorry. You don't even know me. How could you be sorry?
Hi. Oh, jeez. Hi, everybody. I'm Liam, and I speak on behalf of my two guests over here as well. I love sci-fi, and so I was invited by current member Jeff. Honored to be here with all of you. Thank you.
Awesome. Thank you. Oh, you're even close. This is like who says prayer doesn't work.
Thank you. Hi, I'm Lissa. And we just say why we joined?
Yeah.
Oh, hi. I love space a lot. So excited to be here. Yeah, seems like the right place. Nice to meet you all.
That's right. Here we love space and climbing stairs. That's the two things that we do the most. At least me. Okay. Hi, Zoom. How are you? I'm thinner than I was last time you saw me. Okay, so the agenda for today, we did the first one. We're going to get right to our guest speaker. Then we're going to do some announcements. I'm going to announce the member that I'm the most stoked about in my Good Heavens report. We're going to give away some stuff. And then I'm going to tell you all the cool things that you can do with astronomy. Not in life in general. So, with no further ado, I'd like to introduce James Thompson, who will introduce our speaker.
Dr. Karen Meach first got interested in astronomy from the original series Star Trek, and it's only been downhill from there. She got her undergraduate degree from Rice University and finished a PhD at MIT. She's specializing in astrobiology at UH Manoa at the Institute for Astronomy and has been there for, probably a lot longer than I've been alive. Although looking out at this crowd, that's not saying a whole lot. She has received numerous prestigious awards across her career, such as the Heaps Prize in Physics, the Andy Jump Cannon Award, the Harold C. Urey Prize, the William Tyler Olcott Distinguished Service Award of the AAVSO, the IFA Director's Research Excellence Award, the UH Regents Medal for Research Excellence, and ARC Science ARC's Scientist of the Year, in addition to 2 NASA Group Achievement Awards for work on the Epoxy and Stardust Next mission, and most recently, the Danny Heineman Prize in Astrophysics, and was elected Fellow of the American Astronomical Society. Oh boy, I wish I could have someone say all those things about me. Wouldn't that be nice? Bet, do it. I first met her because I am studying astrophysics at UH Manoa, and most recently she was my professor for astrobiology and solar system astronomy, and they were both very interesting classes that I am glad that I took. And so you'll be hearing most likely a good summary of the things that I had to learn over the last 6 months. So I hand it back.
Okay. Well, I'll give it over to Dr. Meach. Are you ready?
Yep.
She's
Thank
ready.
you so much, James, for the nice introduction. Whoops. I'll share again. Share on screen. All right. So today's topic, I'm going to be talking about forming a habitable solar system. I was debating whether to talk about this or interstellar objects, but I had to give the abstract quite a while ago. And of course, there's been a new interstellar object discovered since then, so I'll touch upon that at the very end. But I thought I'd start with just a few slides on what I, as an astronomer, do, because it's a variety of things. I used to actually look through telescopes, not quite in this style. This is at Lowell Observatory. But I used to love traveling to telescopes and actually getting your hands on them. Of course, that's not the way it works for me nowadays. I got involved then in a lot of space missions. Most notably, the first one I was involved with was the Deep Impact mission with Principal Investigator Mike Ahern. And this is where we were hurling 2 spacecraft towards a comet and had an impactor to do an active experiment. And after that mission was done, we had the opportunity to take the parent spacecraft and fly it past another body. Now, remember very distinctly at a NASA review panel in front of a congressional committee, Mike Ahern gets up and they said, "Aren't you worried? You picked a target that's only been seen twice before." And he said, "No, Karen Meach is the observer. We will find it." And of course, this picture here is what I was feeling like. Mike, please don't say that. Comets can disappear. And sure enough, it did. It turned out that while we were at a team meeting, we really worked hard to find the comet. It probably broke apart and disappeared. And at a team meeting, someone said, "Hey, Karen, an amateur astronomer has found the comet and reported it on the web." I said, "There's no way." And so this is how I felt. It turned out this person was faking the observations to get some attention. So that's some of the stuff I've worked on with missions. There's also a lot of committee work as an astronomer, and I was in fact on the committee for the International Astronomical Union when they decided to boot Pluto out of planetary status. And I was on that committee. I remember shortly thereafter giving a talk to school-aged children. Talk about a hostile audience when you said you're on the committee that booted Pluto out. I've run lots of conferences, sometimes at big, elegant hotels, sometimes small, intimate settings, such as this one in Iceland. And you deal a lot with workshops with students, postdocs, and other folks. So it's a really interesting career, but the part I like the best is the chance to actually use telescopes and go observing. I spent a lot of my career both using the telescopes on Mauna Kea, Chile, and in Arizona, but I have used facilities in India. So it's been about 35 years of big telescope observations. And of course, nowadays, you're mostly using these with Q observations, meaning you plan the observations, don't have to stay up all night, and someone else does the work. But I do fondly remember the days where, back in the days when I used to go to Chile a lot, it would take, from Hawaii, it takes a good 2 to 3 days to get down there. This is the Cerro Terrenal, where the very large telescopes, these are each 8 meters in diameter. I had an observing run down there. This is my colleague showing off the scale of the instrument for this telescope. So 3 days travel to get down there. We had 2 nights, and we sat in the control room and watched the weather for 2 nights because it was completely cloudy. And of course, the day you leave, it looks like this. So there can be frustrations also. But the real excitement comes when you're involved with some space missions. I was on the Deep Impact mission. I've already mentioned this. My role was to coordinate all of the observers worldwide. So each place where there was a red dot, I was coordinating the telescopes as well as a space telescope and other assets in space. The rest of the team had the excitement of going to the Jet Propulsion Laboratory where they're waiting for the impactor to hit. But I got to see sunset, and it was a beautiful evening, and we had a very successful mission. Another aspect that I've really liked has been when we started to get into astrobiology, and that's what I'm talking about today. And this is a field that some people laugh at because they say, is there really a field because you haven't yet found life elsewhere? But it's more than just about finding life. It's about looking at the conditions for life. And one of the themes that I study in astrobiology is, where did Earth get its water? And this workshop was one of the most memorable I've ever had. I asked about 20 people, half of whom were complete strangers. I said, I've got funding. I'll bring you to Iceland for a workshop. I wanted the best in the world at geology, geochemistry, astronomy, all sorts of diverse fields. We intermingled talks. Notice this scientist here is holding a glass of beer. We worked well into the evening on the talks. We went out and did geological field work in the Icelandic environment. And some of the group stayed up even later, up until midnight. These guys are sampling some glacial ice that they harvested and brought into the hotel restaurant. And they were very gracious to put it in the freezers. This is Steve Moishes harvesting the ice. But some of the late night sessions were spectacular. So this is sort of encompassing what I do as an interdisciplinary scientist. So let's talk about the theme of how did Earth get its water? And let's start with the fact that life requires water. You know, biology's, the cells in our body are mostly made of water. Energy of life is the chemistry that requires water. And it's in part very special because it stays liquid over a wide range of temperatures. Now, if you ask kids where water comes from, they'll raise their hands. Oh, it comes from the oceans, rivers, lakes, streams. And I'll say, but wait a minute, that's where it is. But where does it ultimately come from? And the kids are usually sharp. They'll go, oh, you're an astronomer. It must come from space. And in fact, water does come from space. It is made in these cold, dark clouds, the regions of star formation. There's lots of little tiny dust grains that are expelled from stars. And in these cold regions in space, water actually forms on the surfaces. So really what I'm talking about when I talk about how do you get water to a planet like Earth is, how does it arrive at Earth and in what form? So let's take a look at water and astrobiology. So again, astrobiology is seeking how you make a planet that could have life on it. And that's going to involve bringing the ingredients necessary for life, water, organic compounds. We think you need a rocky planet, and it's got to be at the right temperature. So as of today, we're getting a nice glimpse of the process of building another planetary system. This is a facility in Chile called the Atacama Large Millimeter Array, very high elevation, about 5,000 meters. And it's starting to get images like this one in the upper right. This is of a young planetary system that's forming. The sun, the young sun is in the middle, and these dark lanes may be regions where young planets are growing. Unfortunately, the scale isn't quite right for us to look at habitable worlds, because Earth is a habitable planet, 1 astronomical unit from the sun, so about 93 million miles. And what we really want to be able to do is hone in on that scale in another solar system. We can't do that yet, but probably with the next generation of radio telescopes in the 2030s, we will be able to zoom in and watch planets forming and maybe even look at their chemical signatures. So as of today, we know of almost 6,000 confirmed exoplanets, of which about 4,500 are actually planetary systems with more than one, and maybe 50 of these are potentially habitable. This image here is a cartoon that was drawn when the TRAPPIST-1 system was discovered, which has 3 planets in the star's habitable zone, meaning they could have water, liquid water on the surface. So, is there something special about our solar system? You know, we're the only example of a solar system that has a habitable world that is in fact inhabited. So of course, everyone knows the architecture of our solar system. We have the rocky planets close to the sun. The habitable zone right where Earth lives goes maybe almost inward to Venus, almost outward to Mars, big asteroid belt, and then the giant planets. Is there something special about this architecture that enabled us to have life? Well, in fact, when you look at the distribution of planets that have been seen around other solar systems, and this is a few years old, but it shows the main points. If you look at how quickly they go around the sun versus how big they are, you can see most of the planets that are on this graph are large. They're Jupiter, Saturn, Uranus sized, but they're very close to their star. Now, part of this discrepancy, it's really difficult to see things as small as Mercury and Mars, so that could be a bias. But we don't seem to have any of the planets that are in this region of the diagram. So the question is there something special about us? So we want to explore how our solar system became habitable. We've got to go backwards in time and look at the leftover pieces of that process. And so the best way to do that is to look at the fragments that never made it into the planets. So things in the asteroid belt, not the rocky bodies. We like the ones that still have some ices because that gives us a glimpse of the chemistry of the early solar system. And we also want to look at things that are much more icy, the comets that may have formed near the giant planets and got kicked out into the outer solar system. So let's start with, again, looking in more detail at what life needs on the planet in terms of water and organics. Water is the most abundant molecule that can freeze out at low temperatures in space, where stars form. So if we were just going to take a clump of interstellar material, you would expect that planets would be very water rich. But our solar system, the inner part is not water rich. You know, Mercury is really dry. Venus is very dry today, but it probably lost all of its water. It may have had as much as Earth. Although we look like a nice wet world, we actually don't have that much water. Probably in total, less than 0.1% of our mass is water. The moon is quite dry, and Mars is almost dry, but we're seeing more and more water subsurface. The leading ideas about how life formed are saying that you need some water, but you can't have too much and you can't have too little. And in fact, many leading theorists say you really need cycles where you have dry land on the surface that dries out completely and you have wet, dry cycles. And the reason for this is there's all these chemicals that are raining down on the planets from meteorites and materials from space that have what we would call prebiotic compounds, organic compounds that can be the building blocks of more complex molecules. And for them to form these large molecules, they need to be brought in close proximity. And that's where this wet-dry cycle helps. You can get these thin films, and when it dries out, everything coalesces, it gets wet again, and you can start to make encapsulated vesicles. On the other hand, if you get too much water, that's bad news. In spite of movies where you see water world and places where it's an ocean world, a lot of people believe if we had as much as 5 oceans worth of water on the Earth, it would turn off this cycle that recycles carbon dioxide out of our atmosphere. And this would make the world inhospitable for life. We'd no longer have any dry land for weathering to get some of the essential ingredients that life needs. If we had a complete water world, say 50 times the ocean volume that we have now, there would be such high pressure at the ocean floor, you would have a solid layer of ice, and there would be no connection between the rocks and the water, and that's how we get some of the cycling of nutrients. So we need just enough water. So it's starting to sound like the Goldilocks and the Three Bears. So let's look at where we may have gotten our water. And the way I like to start this is let's start with a timeline of what we actually know. And the first date on here is when the solar system formed. And so we peg this at 4.56 billion years ago. And this is the date at which the very first solids condensed out of a cloud of gas and dust. So our solar system started as a big amorphous cloud of gas and dust. It started to collapse. It got hotter in the center. It flattened out into a disk. And then materials were vaporized. And then as more and more material comes in, it starts to cool off, and you start to condense materials. You make dust grains, and you get ices. And so when you take meteorites and you slice them open, this is a microscopic image of a meteorite, false color, you can start to do radiometric dating of the pieces, and they all cluster around the same age. They've also collected samples from comets and brought them back to Earth with the Stardust mission. You get the same ages. The other thing we know for sure is that Earth had ocean water, extensive oceans, by about 200 million years. And so the way we know this is twofold. Sorry about that. Some of the oldest rocks in the world are in Australia. These are 4.3 billion year old rocks, and they have minerals contained within them that were probably volcanic eruptions underwater, and they have preserved the signature of that time. And these can all be dated to about 4.3 billion years ago. Another piece of evidence that we had extensive water at this time is from some of the other oldest rocks in Canada. And what these are metamorphosed granites. And granites must form through volcanic eruptions in water that recycles the rock over and over and mixes with water. And these two show that we must have had a lot of water. So somewhere in this time period, Earth got its water. Several possibilities. One suggestion was, well, as the planets were forming, once we've got a flattened disk of dust and gas, young sun is getting warmer in the middle, Earth was forming about 1 astronomical unit from the sun in a region where it was too warm for water to be in the ice phase. It would have been in the gas phase. Outside of that region, it was cold enough that you could make ice. They said, well, maybe the water in its gas form just stuck to the little ice grains. That's possible, but we don't know if it would be enough. Another idea is early in Earth's history, Earth went through several periods where the whole surface was molten, a magma ocean. If we had gas in the form of hydrogen in our atmosphere at that time, it would chemically combine with the oxygen in the rocks and actually make water on the surface. Then a final idea is, well, all right, it's hard to get water accumulating on Earth, but what about outside this ice line where it's really cold? Couldn't things have hit the Earth that came from the outer solar system and brought the water to us? And we certainly see examples that things hit the inner solar system a lot. Here's an image of the moon with impact craters. This one is Mars. This crater looks a little bit odd because it apparently impacted a region where there was subsurface ice, and then it kind of flowed in a slurry of mud as the crater formed. And then this is one of Jupiter's icy moons with a chain of craters. So clearly things were hitting all over the solar system. So how are we going to tell these scenarios apart? We need some sort of metric to evaluate. And so one idea that actually occurred in the 1980s was people had noticed that the type of water in Earth's ocean was enhanced with deuterium. Now, every atom can have an isotope, which means instead of just having protons in the nucleus and electrons surrounding it, there can be neutrally charged neutrally charged particles in the nucleus that will not change the chemistry, but it will change the weight. And so when they measured how much H2O, water, versus heavy water, HDO, it was much higher than people expected. And their expectation was set by looking at the gas in nearby solar systems in the interstellar medium. So they said, interesting, the Earth's oceans are about 6.5 times elevated in deuterium. So then in the 1980s, the European spacecraft flew a mission to Comet Halley. This was called the Giotto mission, and it actually flew through part of the dust and gas tail of Comet Halley, and they made a measurement of the D to H in water. And what they found for Comet Halley was that it was high. It was elevated by about a factor of 2 over Earth's ocean. And this set everybody, they were all excited because maybe this is where Earth got its water. This might be the burning flame that says it was material from the outer solar system comets that smashed into Earth. As a few more comets got measured, this time from the ground, they too were high. So everyone's excited. But that's not the only thing that hit Earth. Asteroids would have hit Earth, meteoritic material. And when you look at the measurement of D to H in the leftovers from asteroids, you can see there's a range of values, some of which match Earth's oceans directly, some of which are too hot. So how are we going to detangle this? Well, let's take a look at each piece of this, if you want to call it an equation. And let's start with, do we really know the starting value of D to H from our solar system? Before they had beautiful images like the underlying image here from the Hubble Space Telescope of young solar systems forming, the chemists were working hard at calculating how much heavy material there should be with the deuterated species. And what they found was at low temperatures, it is much easier to, it's much more energetic, just starting to form, you're going to have a lot of deuterium. So this fit nicely with the idea, well, comets are formed cold. Maybe that's really what brought in the water. However, as people got more and more sophisticated models, they started to actually map out the structure in the disk. Remember, I said it's a flattened disk, hot sun in the middle. It flares out at the outside because it's collapsing more slowly. They said that the surface layer here is going to be rather warm because it's heated by the sun's energy. The middle portion is going to be cooler, and that's where you're going to get a lot of molecules forming. And then at the midplane, it's going to be very cold. So one might naively expect, okay, all the heavy deuterated species are at the midplane. Then we got really sophisticated models, and it looks kind of like a mess. This is where the sun would be. As you move farther from the sun, Jupiter, Saturn, out to Neptune distances, you can see it's not just deuterium increases the redder colors as you get far from the sun. It's kind of a mess all the way through. So the idea that we can say the initial solar system had a single value of D to H at a specific time, I think we just have to throw that out. We really don't know what the solar system started with, and we don't yet have the telescopes that can observe this in detail in other solar systems. What about the comet measurements? How are we doing there? Well, you can either use a spacecraft, as Giotto did, or you use ground-based telescopes. And the very first two that were measured from the ground were done from Mauna Kea. This is a beautiful image of Mauna Kea. They were done using the, I think the JCMT telescopes, which is over here. But they only measured the hydrogen and the deuterium with that. They measured the oxygen with another experiment on another day, so it had a large error bar. So you could only do this with really bright comets. And so after several years of hard work, a handful of comets were measured, and they were all really high. So people are thinking, well, that's kind of dooming the scenario that comets brought it. They really don't match the Earth's oceans. Then we got a measurement of a different type of comet, 2 comets. These were ones that we figured formed in a different part of the solar system. And aha, this line here is the Earth's ocean value. Maybe these are the type of comets that brought ocean water because they formed in a different region in our solar system. And so people were eagerly awaiting the European mission to the Rosetta mission that went to Comet 67P, because this one was the same type of comet as the short period comet. And it had the highest D to H ever measured. So scientists threw up their hands and said, forget it. We just don't know what comets are telling us. It's a mess. They're all over the place. So we will put a question mark by the comets. What about the meteorites? Those, we've got samples. We've got thousands of samples. These are fragments of larger asteroids, and you measure them in the laboratory. This is what's called an ion probe, big, expensive instrument that can actually make very precise measurements of chemicals in tiny portions of the meteorites. And what they found by doing these experiments over years, and this is a little faint to see, but you get a histogram from various meteorite types, and they all peak in D to H exactly where the Earth's oceans peak. So you think, why aren't we done? Clearly, it's the meteorites that brought the water. Unfortunately, they also bring other things, and some of those other chemicals really did not match the Earth. So, I guess we have to confidently put a question mark by our meteorites. What about the other side? Surely we've got a good measurement of Earth's oceans, a lot of water there, you can measure it infinitely many times. But it occurred to one of the scientists at UH, what if this isn't the water to measure? And that had always bothered me because a lot of things happen to ocean water. It evaporates, you get rain, it gets subducted when you have plate tectonics. There's a lot of processing. Doesn't that change the deuterium and hydrogen ratio in that water? So the first exercise was to say, well, how much water is on the surface versus inside the Earth? And the chair of oceanography here at UH wrote a very nice review paper. And he started with, okay, we can measure how much is in the oceans and atmospheres. You can make an estimate of that. And so we've got two columns here, one with low estimates, one with high estimates, and here's how much you could have. And they're all the same because this is just a measurement. As you go deeper into the Earth, it becomes less and less certain. So you can see in the crust, there's a difference of opinion on the low and the high. The crust could hold that much in the minerals, and this is in terms of ocean volumes of water. So we get deeper and deeper, you can see the divergence is greater. And if you add up the columns, the people who are on the low side say we may have 1.5 oceans of water on and in Earth. On the high side, it might be 11 oceans, but we could potentially have 60 oceans of water. My colleague felt it was more like 3 oceans. So this got me thinking, if there's more water inside the Earth, are we really measuring the right water? I went to an astrobiology conference in Iceland in 2004. And like many of these conferences, you get a chance to go on a field trip afterwards. And I picked the one to northern Iceland. And one of the places we got to visit was shown in this picture here. It's a geothermal field. And the geologist said, it's okay. That's just water. It's cool. It's primordial water. You can go over and touch it. And of course, my light bulb in my head went up. Primordial water. That's what we need to measure. Something that hasn't changed, like the ocean water. So I got really excited. I went to the University of Iceland and talked to some geologists afterwards. And they said, well, that geologist was completely wrong. This is water, but it's just rainwater that gets down and gets heated up a little bit by the geothermal and comes out as steam. So I was all despondent. And he goes, but wait, we do have evidence of primitive material coming from the deep Earth. And this is coming from the boundary between the core and the lower mantle. And it's coming up in special regions like Iceland, like Hawaii. And we know that it's primitive and it's never mixed with the inside of the Earth based on the helium ratios, the isotopes of helium. And I said, wow, has anybody ever measured the D to H of this water? And they said, no, it'll be a really hard experiment. And you'd need one of these brand new ion microprobes. And I was all excited. I said, University of Hawaii just got one. And so that led me onto a diversion in my career where I'm out finally doing geological field work. So I go out with a volcanologist and I was kind of dismayed. Here we are in the field. I was taking a picture and I said, oh my God, all the rocks look exactly the same to me. How do I know which ones are important? And they said, well, That's why you have me along. I said, well, that's not a very good teaching moment. You have to instruct me on which ones look good. He eventually did. We collected a bunch of rocks. You make thin sections. And what we were looking at, this is a millionth of a meter here, micron scale. You're looking for inclusions in these rocks that would have erupted underground under high pressure that still have their primordial water, and you measured that water. And so we had a postdoc that did all these measurements. I just helped with the collection of the samples. And what she found was that the Earth's interior water is very different from the ocean water. It has less of this heavy hydrogen, so it's less deuterate. Okay, so now we've got our schematic of how to figure this all out, and I put question marks everywhere. Now what? You know, have we just made a complete mess of things? Now we don't know what's going on at all. Well, let me pause here and give you some takeaway numbers. And I know this is being recorded, but just don't write these down. We haven't had a press release or anything. I think we probably have water from a lot of sources. I think it's probably from comets, from asteroids. It may have formed with the Earth. It may have formed on the magma ocean. And it may be a matter of how much we get. And I think probably the study of where it came from is going to be the really interesting story. But I know everybody always wants to see how much do we think is coming from each source right now. So here are the numbers. Don't share these numbers. I apologize, I've got so much precision here, but I always tell my students don't put too many significant figures, but this is exactly how much we think is coming from each of these sources now. So now what? It seems like we're kind of in a conundrum. We had a scheme to figure out where water came from. What are we doing? Well, actually building a solar system is a very complicated process. You've got, this is a cross-section of what our young solar system may have looked like. It's a flared out disk. It's hot in the middle. So the different colors represent the temperatures. It's the temperature that sets the chemistry. And you've got dust grains all through here. And so the ices are being influenced by the chemistry and the temperature, and they're condensing on the dust grains. But as the dust grows into bigger and bigger building blocks of planets, the giant planets start to grow and they start to throw things around. So things start to move in the young solar system. And this is a schematic showing that we've got some fingerprints and that the giant planets toss things around. So we've talked about D to H, and I showed a map much like this, but that's not the only chemical we can use as a fingerprint. Another one, and I'm not going to go into a lot of detail, I just want to impress, we've got a lot of markers to help us. Another one was oxygen. The cosmochemists, those who study meteorites, were very puzzled by the distribution of the oxygen isotopes. Oxygen has three isotopes. Oxygen 16, which is the most abundant, I forget the exact percentage, 99.7% or so. Oxygen 17, which is the least abundant, and oxygen 18. And what happens is that the ultraviolet radiation from the young star breaks apart the carbon monoxide that we see all over the early solar system, and it frees up the oxygen that combines with hydrogen. So if this happened to be oxygen 16, you make H2O with oxygen 16. That's the most abundant. It absorbs all the UV close to the star, and now the only ones that can break apart are the rare isotopes. So you get this spread in isotopes in the solar system. That's got to tell us something about where the water came from. You can play the game with nitrogen and noble gases. So I think the message is to really understand what's going on. It's not just one chemical, you've got to look at them all. So now it's been made much more complex. About 15 years ago or so, there was a really interesting discovery that the cosmochemists made when they were studying iron meteorites. And they were looking at meteorites that were various primitive forms that probably formed a few million years after the early solar system had condensed. And when they measured isotopes of titanium and chromium, instead of just a mixture all over the place, there were two distinct groups. And this seemed very peculiar to them. because they get their isotopic signature when they're tiny little dust grains. And when things are dust grains, they tend to drift inwards towards the sun very readily. So what they didn't understand is, how do you keep these two groups from mixing? So their suggestion was that maybe Jupiter formed really early, grew big really early, and made a gap. And so their idea was that first you start with an even mixture of material. Jupiter formed early after about 4 million years, started to make a gap. And then a supernova went off nearby, polluted the outer part of the disk with some new material. And this couldn't flow inwards anymore because Jupiter's in the way. It was only after Jupiter got really big that, as these building blocks clump into bigger and bigger pieces, that now Jupiter can fling things over gravitationally. They don't drift in under sunlight. So the idea was, well, maybe Earth, which grew inside Jupiter in this hot part of the nebula, just managed to get its water from the gases in the inner disk, or Jupiter threw it across the gap and we got our water that way. So we can test this, because anything that Jupiter tossed inwards would have hit Mars, Earth, Venus, Mercury, and it would have gotten trapped in the asteroid belt, where we can still see it today. So it turns out that in the mid-1990s, there was a discovery of something called main belt comets. And what these are, they're things that are very firmly in the asteroid belt. They don't have comet-like orbits, but they had comet-like tails. And every time they got a little bit closer to the sun, they developed a tail, which means they have ice in them. And so the idea was, these were tossed inwards early in the solar system's history. If we can go measure those ices, maybe we get a hint of, does that match Earth's water? And if so, now we have our solution, that the giant planets tossed things from the outer solar system. These things are so weak in their activity, we cannot observe the isotopes from Earth. You'd have to send a spacecraft to go look at these bodies. So if we did, that would get at the chemicals and tell us a little bit about the chemistry, but we still have the missing piece of, where did they move from? How do we understand the movement of the early solar system bodies? Well, I wanted to give you a look at the family of small bodies that we can study. You've probably heard of all these different comet classes, but didn't know their relationship to each other. We've got the long period comets that have very long periods, come from the outer solar system. Halley type comets, we've got short period comets. We have centaurs that are leaking in from the region beyond Pluto. But we've got a whole new suite of objects that have been discovered in recent years that are of interest for telling us about solar system formation. And I want to talk a little bit about this group. They're called the Manx comets. So it turned out in 2013, the Pan-STARRS Survey Telescope, shown up here on Maui, discovered an object on a long period comet orbit, and the Pan-STARRS principal investigator came into my office and said, Karen, we found an object that looks like it has a long period comet orbit. It's close to the sun, but it hardly has any tail. This is what it looked like. Is that interesting? And I said, oh yeah, because like a long period comet that's that close to the sun should look like this. Something's really bizarre about this guy. And my initial thought was, maybe this is solving a mystery that we've had since the 1950s. We decided to call these Manx objects, instead of saying object on a long period comet orbit with hardly any tail. Manx is the form of a tailless cat, so that makes it less of a mouthful. So we have the Manx comets. So what was the mystery that I was excited about? Well, in 1950, a theoretical astronomer, Jan Oort, had postulated that our solar system was surrounded by this vast cloud of small icy bodies, comets. And the way he figured it out was he looked at the orbits of, his experiment only had 18 comets, And he plotted the number of comets versus their semi-major axis, which is half of the long axis of their orbit. And he found this really tall spike. He said that has to be a source of a lot of objects. He was a little bit upset, though, that it was so narrow, because he said if one of these came into the solar system, it would pass by Jupiter or Saturn, its orbit would change, it would lose energy, it would change its shape, and so they should fill in this region, but they're missing. So he thought maybe they just lost their ices. So we thought maybe we found one of his lost comets. So we took a spectrum. Now, all comets we've ever seen are just red. If you take a spectrum and you divide by the color of the sun, it means they reflect more red sunlight than blue sunlight. And so on a plot like this is the blue end, this is the red. It should just be a straight line going up to the right. Clearly, this looks different. All the colored points are the spectrum of this first mass. Wow, this was exciting because it looked like rocky inner solar system material, but it has a tail. And the exciting thing about this was that maybe we are in fact seeing something that is forming right near the ice line. And, several models predicting how solar systems form, saying maybe the giant planets, this is early on in the history of the solar system. After about 4,000 years, the giant planets have grown. These are the planetesimals, the building blocks, kilometer scale objects. Anytime they get near the giant planets, they get tossed inwards and outwards. The blue and purple colors are icy bodies. The orange ones are rocky. If these giant planets moved a lot into the rocky inner solar system, maybe they tossed some of this material out to the Oort cloud where we see it today. Other models say, nope, you don't need to move and you can still get material out there. So I think looking at these main objects may help us unravel the early solar system. So we've got a big campaign to actually look for these things. Pan-STARRS, this is the detector on Pan-STARRS. It's an enormous CCD. Each one of these tiny little windows is an individual CCD. They're all connected together. And so it can scan a very large fraction of the sky. The full moon would be a large portion of this. So we're actively looking for these, and then we follow up with observations with large telescopes to get spectra. The floodgates are going to open up really soon. We've got the Pan-STARRS survey. We've got the Atlas survey in Hawaii. This is a series of, I think it's up to 6 small telescopes now that survey the sky for moving objects. This one is surveying the sky to look for supernova, but it also finds moving objects. And of course, I'm sure everyone has heard about the Rubin telescope and the Large Synoptic Sky Survey that's going to start at the end of this year. It's an 8-meter telescope and the floodgates are really going to open. So we've got the dynamics that we're studying from Earth. But again, to get back to the chemistry, I think we have to have a mission. So when I've given this talk before, I said, well, missions are expensive. I work on proposals for $500 million to $1 billion projects. And people say, whoa, why would you spend that much? I said, well, let's look at the actual cost. These are some of the previous comet mission costs. They total up to about $4.5 billion. These are some of the other missions. The Apollo mission was $24 billion at the time. If we did it now, it would be $130 billion. Saturn mission was expensive. They talk about Mars missions, humans going to Mars. I think the estimate is much higher. So I've asked people, how much do you think it would cost you for one of these missions to go to a main belt comet and look at the origin of Earth's water? So if we take this estimate of the US taxpayers, divide by the mission cost, each person would have to dedicate $5.40 to the mission for us to figure out where Earth's water came from. I've given a version of this talk for kids, and so I say, this is what you'll give up. Everyone, kindergartners, second graders, they're all unanimous. Absolutely, they would give up this much. If there's teachers in the room, I say, this is what you will give up. And then it's kind of 50-50. Teachers don't want to give up 1 cup of coffee. And the kids scowl at them and say, we will pay for your single cup of coffee. So in the end, I think it would be a great investment to actually find out where Earth's water came from. So I think it's going to be an exciting journey to understand where Earth's water came from. It's a very interdisciplinary discussion, exploration, and that's what makes it fun. As an astronomer, I started out studying comets. You get more specialized in that, but now it's an open funnel. I'm learning about geology, geochemistry. I've gone on expeditions to Iceland to look for rocks that all look the same. So I think we need to go to one of these things along with all the telescopes on the ground. And I think this has huge implications because it tells us a little bit about what are the chances for life elsewhere. So that's what I've got for the origin of Earth's water. But I do have 3 slides if people are interested, since interstellar objects are in the news right now. But maybe we start with questions on origin of Earth's water.
All right. Who do we got local? There's got to be some hands. Yeah. All right, let's do this. Jeff, right?
Fantastic talk. Thank you so much. How many Manxes have been discovered? Is it just that one, or are there more?
We have 2 that have the spectral signature, but we've seen maybe a dozen or so that are on long period comet orbits with no activity, but the others just look red. And so those could be just quartz comets that have lost their ices. But there's 2 that seem to have this interesting feature.
My name is Jeremiah. Thank you for the great lecture. In regard to exoplanets, if we can figure out where Earth's water came from in our Milky Way, could that help us target exoplanets that might have the same signature of creating water with like Jupiter and big planets flinging water inward and outward around a sun? Is that something we can find in other galaxies, and maybe they might have exoplanets there?
I understand your question. It is a complex problem. And my initial thought was, if we do require Jupiter, Saturn, Uranus, Neptune, our giant planets, if you require them to be far from the star in order to mobilize this material inwards, then that is an interesting outcome, which might say it's harder to have a habitable world elsewhere. Because so far we don't see a lot of planetary systems with gas giants very far from the star. Part of that is a selection effect. On the other hand, I personally think it's probably a combination of things, but you have to do the experiment to see where you go to scientifically. So I think it may help us understand the probability of habitability elsewhere.
Anyone else in-house questions? What about online, Spencer? You got anything in the chat?
Yeah, there's one from Laura May. Was the sampling area north of Iceland
It's pronounced Namafjall, geothermal area.
Okay.
This was in 2004. I don't remember exactly where it was. It was near Mevatten.
Okay, yeah, that's probably that one. Cool.
She was awfully cavalier about, just go walk right over to it. It's like, okay.
Yep. All right. Anyone else? Questions for Dr. Meach? Going once. Oh, we got one way at the top, of course.
Yeah, I had a question, but it's regarding interstellar objects. Is the only metric for defining an interstellar object that it's on a hyperbolic trajectory? It was kind of bugging me. How do we, if we find these hyperbolic objects, how can we tell, oh, this is interstellar, came from outside the solar system versus it's an Oort cloud object that got enough energy to make escape velocity from the solar system?
No, that's a good question. We see every year you see quite a number of comets that have an eccentricity slightly bigger than 1. The largest that I know of that is for sure part of the solar system is, I believe, Comet Bowl, which had an eccentricity of 1.05. But there, what they can do is they can integrate the orbit backwards in time and see that it made a close passage to one of the giant planets and take out that effect. So the first ISO 1I, Oumuamua, had an eccentricity of about 1.2. The next one had an eccentricity of 3, if I remember correctly, about 3.6. And the new one has an eccentricity of 6.2. So, these are really on hyperbolic trajectories. And, if you want, I could say a few things about the 3 objects.
I think he does.
Okay. So the first interstellar object, Oumuamua, was small. It was only about 100 meters in radius. It had no apparent tail, and it had a really huge brightness variation from rotation, which suggested that its axis ratio could be 10-1, which is just unheard of in the solar system. So after this discovery, it was discovered by Pan-STARRS in Hawaii, and I led the team to characterize it. I got invited to give a TED Talk, which was enormously daunting. I'd heard about TED, but I hadn't really gotten involved with it. They asked me in November for a TED Talk in April and said they wanted a script by January. I said, you've got to be kidding. Even a good talk just takes maybe a couple of weeks to prepare. At the end of it, I said that was way too little time. It's daunting because you've got an audience of 2,000 people. All the people in the SOFAS region here have paid $100,000 for their ticket. It's higher now. And the cheap seats towards the back are $10,000. Your first day for the dress rehearsal, you see the kind of computer setups, and they've got cameramen everywhere. You go, oh, this is a really big deal. So like a true scientist, after giving the TED Talk, I made a graph of views on the TED Talk versus various publication like Bialy and Loeb alien papers, the second ISO being discovered. No big deal, didn't influence that. I didn't update it for today, but it's been very interesting following just the viewership. So the first one was small, red, dark. The second one, and this is HST true color image of it. The second one actually looked like a comet. Its chemistry was very similar to comets, but it was a little different. It didn't have as many carbon compounds, although we do see carbon compound depleted comets in our solar system, but it was really rich in carbon monoxide. So that was interesting, slightly different chemistry. But, you've got a sample of 2. It doesn't really tell you about the other solar system, and we tried really hard to trace its path backwards to its home solar system. But we found that you can't do that, and it's probably impossible, because while you can get its path very precise with position measurements as it comes through our solar system, what we don't have measured precisely enough is the position and velocity of all the stars it would have passed. So that was the status after 2019 with the second one. And then just 2 weeks ago now, July 1st, the third one was discovered. And this was discovered with the Atlas telescope system. So these are small telescopes. I think they're 24 or 36 inch. And it was discovered with their facility in Chile. It was probably the only telescope that could have discovered it. This is a finder chart actually tonight, and it's going through the galactic plane. So it is just a horrible place to try and look for something. We got some images of it right after discovery. It's got a little bitty tail, so it is comet-like. It's not like Oumuamua. We think it's probably pretty big. If you just measure the brightness in the center core here, that gives you an upper limit of about 10 kilometers radius. People have gotten spectra. So this sort of reddish region here is various estimates of the redness of Oumuamua. This region here is redness of the second one, 2I Borisov. And then you can see the spectrum and the dots show the third one. So it looks cometary, just like the others. So we're all scrambling right now to get telescope time. We're using everything that we can on Mauna Kea. People are triggering proposals for JWST. We're trying to get time in Chile on other facilities. So right now it's a feeding frenzy, and people are trying to write papers as fast as they can and get them out to be the first to say they observed X or Y on the third interstellar object. But to be clear, it is not an alien spacecraft, even though Avi Loeb is starting to talk about some strange things also with this one.
Okay. Any other questions? Dave, you got a question?
When the Great Magellan is completed, how is that going to affect your research?
These will be, once you get a 30-meter class telescope working, some of the stuff that took maybe hundreds of hours for Oumuamua to study over a period of a week, you could have done in one night with a 30-meter class telescope. So this is going to be fantastic. Instead of noisy spectra, I mean, this comet's relatively bright. This is about 17th magnitude right now. And this was an 8-meter telescope to get a spectrum. And you can see it's pretty noisy. So you will get superb signal to noise for all of these objects. So I'm excited to see 30-meter class telescopes.
I'm actually excited anytime I get near one of these small 36-inch telescopes that you're talking about. You have any of those lying around in your couch cushions that you're looking to get rid of?
No, sorry.
All right. All right, got one more for Brad.
Hi, could you elaborate a little bit more on why the current amount of water could not be accounted for with natural processes, just given the changes in mass of the Earth, big impacts like even a moon, and then also evaporation of the atmosphere over time? Like, how do we know for sure? Is it just the deuterium percentage, or is there a time factor?
No, it's not so much a time factor. It's the fact that the deuterium is so high in Earth's water. So anything that would have formed out of the gas only would have had a much lower D to H ratio. Anything that had ices in it had a larger D to H ratio. So we're trying to figure out where in the solar system it came from. It's not so much about the amount, it's where it came from. And again, that gets back to the question someone asked about, will this tell us about habitability elsewhere? Because if you need a solar system that has gas giants pretty far out, asteroid belt maybe or maybe not, that's throwing things inward, those aren't so common. So that's why we're trying to figure out where it came from.
Thank you so much for meeting with us. This has been amazing. You've got a room full of people who have telescopes here, and I'm wondering if you would wager a guess as to the maximum brightness we will experience this third ISO from Earth. Is it the type of thing we might be able to see through our own telescopes? Obviously, astrophotographers might be already able to catch it, but is it something we could see with our eyeballs up to a pretty big telescope?
I would wager a guess. We've got, one thing I've been doing is I've got a database of 35, 40 years now of comet observations, and we're trying to get this online, accessible to the community. So the sort of thing we can do is you would pick an object, you'd select a source, pick your object, you'd say, give me the output. This happens to be comet C2017 K2. But it will give you a light curve. All of these, the really dense part of the light curve is from Atlas. We don't yet have 3I in the system, but I've done, with some of our big telescope data, we have just a tiny arc of something like this. I've done some models, and my prediction is I think it's just being driven by water ice. My prediction is it would reach about 10th magnitude in our tiny aperture. I run the model for a 5 arc second aperture. And of course, when it gets close to the sun, the tail and coma is going to be much bigger than that. So naked eye would be a lot brighter. So I wouldn't venture to say if it'll be naked eye, but if the tiny 5 arcsecond core is 10th magnitude, it's going to be a lot brighter than that.
He's gonna look. He's writing it on his calendar.
Well, you know what? If amateurs start to get these nice light curves, also, this helps us be able to model the comet to make predictions of how bright it is. And I've been doing that frantically the last few days because we're trying to put some programs in to use adaptive optics to see just how big the nucleus is. And for that, I need to predict how much light is coming from the nucleus in a tiny aperture.
Yeah. How? Which month will it be at its brightest? At 10th magnitude.
Well, my model predicted that magnitude at perihelion, and of course, at perihelion, it's in conjunction with the sun. But it should be bright. November, December, I would think.
All right, only for the hardcores going out.
These are really good insulators. And so the heat wave will take a little while. If it's water ice that's sublimating, that's turning into gas, that's mostly a surface phenomenon. But if there's any carbon monoxide or carbon dioxide, that tends to be buried deeper beneath the surface, and it takes a while for the heat to get there. So these things can be really unpredictable. So we will see. This thing may have been traveling through interstellar space for billions of years. Who knows? It'll be very interesting to see what happens with this one.
Excellent. Is there any more in the Zoom, Spencer? I see a couple more.
Just one that, let's see, the comet will only be as bright as 13 magnitude, I thought.
Well, what people do when they're predicting magnitudes for these is they take a single data point or 2 or 3, so say something on this curve, and they extrapolate. But you can see that this curve is not going to follow a simple function. And so an extrapolation based on only a few data points often gives you a wrong answer. So I don't know. All I can say is that the model run out was getting to 10 or brighter, but that assumes that this activity is driven by water ice and that it maintains the same level of activity or the same fraction of its area that's active as it gets closer to the sun, and the sun's heat will cause it to warm up faster and faster and push the dust off. So I'd say anybody's predictions right now are likely to be wrong, but I think it has a good chance of being reasonably bright.
Close enough to try.
Yeah.
One way or another. Okay. Anyone else? Hands? Oh, we got one.
Hi. This is going back to your isotope slide. I'm just curious. You mentioned that the UV radiation breaks the carbon and oxygen and splits them up. How did they find that out?
This is from models. They know that UV at it takes a slightly different wavelength if this is C oxygen 16, C oxygen 17, and 18. There's just enough energy. They know the chemists know the bond energy that holds the carbon monoxide molecule together. And then you can just calculate at certain wavelengths, is that enough energy to break it apart? So they do know that this must happen in the disk. And it's just, given that this 16 flavor is 99.7% of the molecules, once you have used up all of that UV light from the sun, then they stop breaking apart. And the only ones you're going to break apart are oxygen 17 and 18, which are really rare. And so in the outer nebula, you'll tend to get a preference for water that is heavy with the oxygen. And this was their attempt to explain what they saw in the meteorites. They saw different ratios of the oxygen isotopes in meteorites. And this was one idea that could explain it. It's not the only idea, but it was one. And so if you've got a lot of different chemical fingerprints, the idea is that you could combine them together to build a nice scientific story. But it's complicated.
All right. We good, everyone? Has the knowledge sponge been soaked? All right. Awesome. Thank you so much. That was amazing. That's fantastic. All right, we can get into our club announcement at this point. There's a couple of things worth mentioning.
I did wash my face with the water as well, but
It's like disgusting and sweaty. And third story.
Maybe a mute. A
little
mute.
frustrating because I have to be there at work at times. So I'm working early in order to.
Yeah, we've changed the location of our meeting. Okay, regardless. All right, so a couple things to note. I'm going to get back to our RZWO affiliation. I have to correct my assertion that our discount code was product line wide. It is in fact only for C-stars, so apologies for that. But you can get your 5% discount. Just reach out to me at president@laas.org, and I'll get you your code, and you can save most of your tax, at least. If you've been C-star curious, but are not ready to take the plunge, the good news is our S30 that they promised us has arrived. So look for that to be at Garvey for you to borrow. And an S50 will likely show up in the loaner program ranks as well. So that's just showing up at Garvey, and then you can walk away with one for a month. And then if you decide you want to buy it, you'll get it a little cheaper than your friends that are not in the club. Yeah. It'll work on any iOS, or it's for iOS and Android. It doesn't need to be an iPad. It'll work on a phone as well. Yep. I mean, it's a little less immersive unless you hold it really close to your face. Yeah. So, yeah, you're good. So, bring your own mobile device. Okay, the other thing that's worth mentioning is actually pretty exciting. Earlier in the year, Spencer and I presented our Lockwood 5 master plan, and I'd like to announce that we have $50,000 of funding for that too. So that's amazing. That's not from a single person, that's from a lot of you, so that's amazing. So we're basically a quarter of the way there, and we haven't even really begun our fundraising yet. Look for me to start talking about that incessantly next month. But it's really exciting. If you haven't gone and looked at a 5-acre property, it's beautiful. It is pastoral, maybe pastoral. You can see where the house is. We kind of like taped it off so you can build the house of our dreams in your mind by looking at it. It's going to be great. I promise. It's going to be amazing. So that is what I have for announcements. Now I'm going to get to my good heavens section, where I like to call out a member of the club that has stood out of late. And for this month, I would like to call out new board member Laura Mae Abron. Yeah. She is a tireless adventurer, kind of like the Laura Croft of our group, who chases tornadoes, volcanoes, and observatories all around the world. I originally asked her to join the board of directors because of her affiliation with Griffith Park, and wow, I'm really glad I did that, because I mean, from everything from changing dates for meetings and setting up Star Party stuff and dealing with the lawn here, she's really on top of it. She's been a speaker. If you guys haven't seen her exoplanet presentation that she gave, I think it was last year or the year before, go back and look online. It was one of my favorite presentations ever. And I believe she's going to be speaking later this year as well. And most recently, she's volunteered to head up the Centennial Committee. So looking forward to that. So thank you very much, Laura. May.
Wait, was this about me?
Yep, that's you. Talking about you.
Okay, thank you.
You're welcome. All right. So let's get into it. Let's make the world greener, one stream of photons at a time, and let's give away some door prizes.
Okay, those of you on Zoom, I've posted the link for the drawing, so please sign up. I'm only 7 out of 25 people signed up, so your chance is really good.
Right at the very beginning. I'm not doing it. They can do it next time. Want to have your moment in the sun here? Okay. Oh yeah, after this, I'm going to do announcements for everything. I've got a big long list of activities. I'm just rallying our base here before I get into that with bribery. Yeah, Spencer's been sponsoring. Yeah, that's good. Yeah. Let's go.
And the winner here for the first one is 833-5260. 5260. Oh, you're kidding. There you go, Bob. All right. And what does he win, Brian? Do we know? Lasers today? Okay, because we do have one red flashlight too, so I know that up there.
For those of you who are on Zoom, if you haven't registered, you've got about another 30 seconds to register before I close it out.
Okay. The next one over here, the second one is 833-5262. 5262? I don't know, is it? 52. You're the winner. There you go. Alan Durr gets it. And the last one is 833-5274. All the way to the top. Congratulations. What's your name? Sandy got it. Okay, we're good.
All right, Spencer, take it away, bud.
Okay, hang on. Give me stall for about 30 seconds.
Where did you say the information about the code to get the door prize?
Well, it's in the chat, but I've already closed it out right now. But okay. Right. Okay, here we go. Okay, Erin Dinnigan is the first one.
Yay, thank you.
Okay. So what does she get?
These are all $50 or less online store purchases.
Okay, so we have your email address, so we'll be getting in touch with you, or Justin will be getting in touch with it for that. Okay, next one is Jose Aguilar.
Yes.
Okay. And Elizabeth Wong.
Hey, there we go.
Hey, thank you so much. I love it. Thank you.
Okay.
Awesome. All right. So from here, I'm going to list our upcoming events. There's always a bunch going on with the club. The next general meeting that we're going to have is on August 11th, but that's a big one. Everybody show up. That's at the planetarium. We get our own very exclusive planetarium show. Bring your good vibes and your binoculars. Last year, it was a real treat. It was always kind of cool to see that many club members together. So show up. It's going to be amazing. Other than that, we're going to have our next Griffith Park Star Party on August the 2nd. Our next outreaches that I'm aware of are going to be Silver Lake this Thursday, as every Thursday. Our next big one with music, which is going to be featuring Mia Day. I just talked to her today. She's going to be playing. That'll be on 7/31. Our next Santa Monica outreach is going to be August 16th. We have family night this Saturday at Lockwood, 7/19. Show up. This is going to be this is the time of year to come do it. It's going to be warm.
Fortnights.
Warmer. We have the potluck. All the scopes are working great. The last couple of family nights have been really special, and I'm sure that will continue. A week later, on 7/26, we're going to have Dark Sky Night, which is just like family night, but with no food and a lot less of the green lasers that you win here. You can leave them at home. Our next, we're going to have our 60-inch night, which is booked up, I believe, but that's on 7/26. And if you are wondering what a board meeting is like, I'm sorry for you, but that is that we're going to be doing that on August 6th online. That's open for all members just to see. There's no skull and crossbones. Come hang out. It's pretty fun-ish. I don't know. We laugh more than once. We make a point of it, actually. Like, see, it's fun. I don't know, I think we're talking to ourselves. And then also the Lockwood Committee is going to meet on August 4th, and that helps to dictate what the future of the property is, which is kind of an exciting time for it because we're still we have our overall view, but if you want to help guide that in the nearer term, we have that. So that's all that's coming up, except in the very near term for anybody that's here and wants to check out that Pegasus Smart Eye. We're going to be giving a demonstration of it right after this, not at Griffith Park, just off there. So meet me after here, and we're going to set it up so you can see what it looks like. The Pegasus Smart Eye, the little. It's going to be we're going to get kicked off the property, so on Ferndale, yeah, just kind of meet up and we'll get the details. So make the hang, see what it's like, and that's it. Thank you, everybody. Thank you, Dr. Meach, if she's still there.
No.
What's that? Yeah. Oh, that's right. We're doing it on August 10th. All right. Hey, for everyone's here, that's right. There's one more thing. I almost forgot to mention it. We're doing our new member potluck and swap meet for all members, whether you're new or old. Come to Garvey Ranch Park on both or medium. I don't know, medium rare, Thousand Island, whatever. Make the hang. It's going to be awesome. Meet fellow members, trade the gear that you don't want, and get the gear that you do want. God bless. We'll get there. All right, everybody. Thank you. Good night.